Above every large thunderstorm, lightning fires upward into space. Not sideways, not down to the ground, up, through the stratosphere, reaching altitudes where the atmosphere is barely there at all. Pilots reported it for most of a century and were quietly told they were mistaken. The first photograph was an accident. This is still unexplained, the science that hasn't finished arguing. So why did it take until 1989 to prove something that enormous exists? What is actually happening up there, given that the air is far too thin to carry lightning the way we understand it? And which parts of it do atmospheric physicists still openly admit they cannot explain? Begin with the prediction, because someone called this in 1925. A Scottish physicist working on thunderstorm electricity reasoned that the electric field above a storm should not simply stop at the cloud top. It should extend upward, weakening with height, while the air itself thins much faster. That ratio is the whole mechanism. Thin air breaks down electrically at a much lower field strength than dense air. So even though the field above a storm is weaker than the field inside it, the air up there is so rarefied that the field can still exceed what it takes to ionize it. He predicted discharges above thunderclouds. Then nothing happened for 64 years. Not quite nothing. Throughout those decades, airline pilots and aircrew flying near large storms reported flashes above the clouds, columns, flares, glows that went the wrong way. The reports were sporadic, unphotographed, made by people who had been awake a long time, and they were largely filed and forgotten. The proof arrived by accident in July 1989. Researchers at the University of Minnesota were testing a low-light video camera, pointing it at the sky to calibrate it, with a distant thunderstorm happening to be in frame. On reviewing the tape, they found two enormous luminous columns above the storm, lasting a fraction of a second. They were named sprites, deliberately, because the researcher wanted a name that carried no theoretical commitment. Something fleeting and hard to catch, with no claim about what it was. 30-odd years later, the name has stuck, and it remains one of the better pieces of scientific naming. Here is what a sprite actually is. Most lightning carries negative charge from cloud to ground. A minority of strokes, perhaps 1 in 10, carry positive charge, and those tend to be far more powerful. When a big positive stroke drains a large volume of the cloud very fast, the electric field above the storm changes almost instantaneously. That sudden change leaves the thin air 50 to 90 kilometers up, sitting in a field it cannot withstand. It ionizes, and the discharge propagates as a mass of fine branching filaments called streamers, spreading downward and upward from where it began. The whole event lasts a few thousandths of a second. They are red because of what is up there. At those altitudes, the atmosphere is mostly nitrogen, and excited nitrogen molecules emit strongly in the red. The blue tinges sometimes visible at the bottom of a sprite come from nitrogen emitting differently at higher pressure. The color is a direct readout of altitude in chemistry. They are also enormous. A single sprite can span tens of kilometers vertically and be equally wide. If one appeared over a city, it would be visibly larger than any structure humans have built, and it would be gone before you were certain you had seen it. Sprites are only one member of a family. The general term is transient luminous events, and the others are stranger. Blue jets erupt from the top of a thundercloud and travel upward as a narrow cone, reaching perhaps 40 or 50 kilometers, and they are blue rather than red because they occur lower, in denser air. Then there are elves, which are not columns at all but rings. A powerful lightning stroke sends an electromagnetic pulse upward, and where that pulse reaches the base of the ionosphere, it lights a disk that expands outward at enormous speed, hundreds of kilometers across, lasting under 1,000th of a second. And the rarest and most spectacular are gigantic jets, which do what sprites and blue jets do not. They connect. A gigantic jet climbs from the top of a thundercloud all the way to the ionosphere, bridging the gap in a single continuous discharge and briefly linking the weather below to the electrified layer above. That connection is not decorative. It means a thunderstorm can dump electrical charge directly into the ionosphere, the layer that radio communication and satellite navigation depend on. Weather at the bottom of the atmosphere reaching up and altering conditions at the top is not how the system was traditionally modeled. There is one more member of the family that is easy to miss because it is not dramatic. Halos are broad, faint, pancake-shaped glows that sit at around 70 to 80 kilometers and often appear a fraction of a second before a sprite, or instead of one. They are smoother and dimmer, and they seem to represent the same field doing the same thing more gently. And then there is the discovery that has nothing to do with light at all. In 1994, a gamma-ray observatory designed to look at distant cosmic explosions kept registering brief, intense bursts of gamma radiation. When the source was traced, it was not deep space. It was thunderstorms on Earth below the spacecraft. Thunderstorms produce gamma rays. The current explanation involves electrons accelerated to near light speed in the storm's field, radiating as they are deflected in a runaway cascade. And in 2011, an orbiting gamma-ray telescope detected the signature of positrons coming from storms, which means a thundercloud can briefly generate a beam of antimatter. Now the honest part, which is where this channel earns its name. The basic physics of sprites is reasonably well understood. The trigger, the field, the breakdown, the streamers. What is not settled is why some storms produce them in quantity, and other apparently identical storms produce none at all. Gigantic jets are less understood still. They are rare enough that the observational record is thin. They seem to favor certain storm types and certain parts of the world. And the question of what initiates them at the cloud top, rather than allowing an ordinary discharge downward, is not resolved. There is also chemistry. These discharges break apart nitrogen and oxygen molecules at altitudes where the products can persist, and modeling suggests they generate nitrogen oxides in a region where that matters. Whether the global contribution is significant compared with everything else happening up there is still being worked out. The observational problem is the reason so much is unsettled, and it is a practical one. To see a sprite, you need to be looking at the right patch of sky, from far enough away to see above the storm rather than into it, in darkness, with no cloud in the way, with a sensitive camera, during the thousandth of a second it exists. Which is why the field leans on two unusual sources of data. The first is amateurs. Storm photographers with modern sensitive cameras now capture these events routinely, and a NASA citizen science project was set up specifically to collect and catalog their images, turning a scattered hobby into a research dataset. The second is orbit. From the space station, looking along the curve of the Earth rather than up through the whole atmosphere, the geometry is ideal. Astronauts have captured sprites, jets, and elves from above, and dedicated instruments have been flown specifically to monitor them, giving the first systematic global counts. Those counts changed the picture. This is not a rare curiosity. Transient luminous events are happening continuously, thousands of times a day across the planet, over every large storm system, and they have been happening for the entire history of the atmosphere. We simply were not equipped to notice. Which returns us to the pilots. For 64 years, people whose job was to fly near thunderstorms at night reported seeing exactly this, and the reports went nowhere because there was no photograph and no accepted theory to hang them on. The prediction existed in 1925, and the observations existed continuously. What was missing was not evidence, but a way to record it. The event lasts milliseconds, and the human eye retains the impression just long enough to be sure something happened and not long enough to describe it. It took a camera sensitive enough and fast enough, pointed by luck at the right sky. There is a useful lesson sitting in that gap. The sky above every large thunderstorm has been doing this for as long as there have been thunderstorms. It is not hidden, it is not distant, and it is not subtle. It is tens of kilometers across and bright enough to photograph from the ground. We missed it because we were looking at the wrong altitude, on the wrong timescale, with instruments built for a different question. There is no reason to assume that has stopped being true about anything else. So the honest state of it. We know what triggers sprites and roughly how they propagate. We do not know why storms that look identical behave differently. We do not know what initiates a gigantic jet. And we are still quantifying what all of it does to the chemistry up there. And every night, over storms nobody is watching, the top of the atmosphere lights up in shapes that were considered pilot error within living memory. It is a reminder that the strangest thing about our planet may not be how much is hidden, but how much is in plain view above a rain cloud, waiting for someone to point the right instrument at it. The universe keeps refusing clean answers. Subscribe and meet the next one, the deepest place we've ever sent a camera.